Okay, we're going to make believe we're on a planet, and at one point we drop some solid object, some dense object, 2 meters from rest, and we observe that it takes 0.4132 seconds for it to fall. Well, then we easily calculate the acceleration of gravity to be 24 meters per second squared, and I reason this out. We get the average velocity, assume uniform acceleration so that we can double the average velocity having started at rest to get the final velocity, and the change in velocity, divide that by the time interval. That's about almost 2.5 times the acceleration of gravity on Earth. So you'd be pretty heavy on that planet. It'd be kind of difficult to move around for any length of time. You'd probably have a deteriorating effect on your joints, internal organs, and so forth. Okay, probably wouldn't be a good place to stay around for long. Now, I believe this is something else. Okay, now, this is at the equator. At the pole, we drop the object, and it takes 0.4003 seconds to fall. Well, that's about 3% less than at the equator. So you conclude that the acceleration of gravity is about 6% greater than at the pole, because in doing a similar analysis, you would divide by the time interval once to get this, and once again to get this. And in each case, you'd be dividing by numbers 3% smaller. 3% is a small number, so when you divide by something that's 3% smaller, you get something that's pretty close to 3% larger. When you do that twice, you get something that's about 6% larger. So we conclude gravity is about 6% stronger at the pole, or apparent gravity. Okay? Now, the difference, if this is a spherical planet, is going to be due to centripetal force at the equator. You're moving around the equator, so that you have a v squared over r giving you a centripetal acceleration. Now, the centripetal acceleration is, well, okay, if you're at the equator, the net force on you is going to be due to gravity and so forth. The net force on you when you're just standing at the equator is going to be your mass times your centripetal acceleration. Otherwise, you wouldn't be moving in this circle. So, your net force is going to be centripetal acceleration, and that's going to be the gravitational force, which is pulling you down, combined with the normal force, which is pushing you up off the ground. And it's going to turn out that, of course, the centripetal acceleration is toward the center, so your centripetal acceleration is in this direction, so your net force is in this direction, so that the gravitational force is going to be bigger than the normal force, so that your apparent weight is going to be less. And it's the apparent weight of this falling object that pulls it downward. Another way of saying it, of course, is that you have a centripetal acceleration when you're at the equator. So in a sense, the ground, once you drop this thing, the ground is accelerating away from the falling object with an acceleration equal to the centripetal acceleration, and the apparent acceleration is then less. Takes longer to get to the ground because the ground has receded slightly as it moves around the circle. Okay, well, the 6% difference amounts at a 24 meter per second squared acceleration to approximately a 1.5 meter per second squared difference in the acceleration. So the centripetal acceleration is 1.5 meters per second squared. And using this, what we want to do is we want to figure out the period of rotation of this planet. Now, the radius of the planet was given. It was somewhat greater than that of the Earth, which is about 12,000 and close to 13,000 kilometers. I think maybe it was 15,000 kilometers because I probably chose a multiple of 5 or something. We have the radius of the planet. We have the centripetal acceleration, 1.5 meters per second squared. We can easily solve for V. And in the case of this planet, I think we get something like 3,500 meters per second, giving us a period of motion of 3 hours. Now, I had approximately 3 hours, but quick calculation, if it's 15,000 kilometer radius, means you'd have a approximately 90,000 kilometer circumference. At 3,500 meters per second, that's 3.5 kilometers per second. It would take you somewhat over 25,000 seconds, which would be 7 or 8 hours. Now, I got that original estimate by comparing this with the speed of motion around our equator, which is around 1,000 miles an hour, which would be around 400 meters per second, and that's about 1/10 of that. That should give us about 1/10 of the time, but with the greater circumference, a little less than that. That comes out again around 7 hours. So I'm not sure where I got the 3 hours. I made a bad estimate there. Anyhow, you should solve this problem, complete it, and see if you agree with these results. Okay, I'm back to my original estimate. I was using the orbital diameter as the orbital radius, one of the easiest errors to fall into, and apologies, but that's where you'll come out. Now, there is one other calculation we did here. Having found the acceleration of gravity, we could find the mass of the planet, knowing its radius to be 7,500 kilometers, or 7.5 times 10 to the 6th meters. Since by Newton's law of gravitation, G is equal to gravitational acceleration is equal to universal gravitational constant times the mass of the planet divided by the square of its radius. We solve for m, and we get this, and we plug in the radius here squared, the acceleration of gravity here, and the universal gravitational constant down here, and we come up with an estimate of the mass about 2 times 10 to the 25th kilograms. Okay, the mass of the Earth is about 6 times 10 to the 24th kilograms. It's about 3 times the mass of the Earth, slightly bigger radius, and somewhat less than 3 times the acceleration of gravity. So that all kind of hangs together all right. We also wanted to find the orbital velocity 2,000 kilometers above the surface. So the radius of that orbit would be 7,500 kilometers plus 2,000 kilometers. 9,500 kilometers, or 9.5 times 10 to the 6th meters. And we plug that in for R with the mass that we just found in the universal gravitational constant. We easily calculate the orbital velocity. And from that, we could calculate the orbital period easily enough.